Hi, this is the section on 5.1 polynomial functions. Our objectives are going to be to identify polynomial functions and their degree, identify the real zeros of a polynomial function and their multiplicity. Let's start off with the definition of a polynomial function. A polynomial function in one variable is a function of the form f of x is equal to a sub n x to the nth power plus a sub n minus 1, x to the n minus 1 power plus so on. We call this an ellipses. It just means it continues so on. And then plus a sub 1, x to the first power, and then a sub 0. Notice that this one doesn't have an x, but you could pretend there is an x to the 0 power there if you really wanted to. So that way you can see what the power is. Where a sub n minus 1, and so on, a sub 1, a sub 0 are constants called the coefficients of the polynomial. N is greater than or equal to 0 is an integer. This represents like our power values that we had up here. So if you notice here where I put the 0 on this x and the 1 and then a raised to the n minus 1 power and then a raised to the nth power, these represent the integer values where n is greater than or equal to 0, right? Is an integer. That means you cannot have any negative numbers up there, and you can't have any numbers that are like fractions or numbers that are inside of radicals or numbers that are, you know, just decimals or they have to make sure they come out to an integer value that is greater than or equal to 0 for your powers, basically. And it says here x is a variable. If a sub n is not equal to 0, it is called the leading coefficient, and n is the degree of the polynomial. The degree is basically just going to be your largest power on your variable. And the domain of a polynomial function is the set of all real numbers. I think I've mentioned this before in my classes. Any polynomial function, the domain will always be the set of real numbers. We like polynomial functions. These are our nice functions. Now, before I go on, you should know a little bit about polynomials before we move on to the next problems. What should you know about polynomials? Well, you should have learned in your algebra classes, when you're working with polynomials, right, you can only combine things that are like terms. Like terms have to have the exact same variable, raise the exact same power, right? So I've got an example here, a monomial. Definition of a monomial. A monomial in one variable is the product of a constant and a variable raised to a whole number power. And that's basically what we had written before, whole number power. It's a number that is greater than or equal to 0, and it's an integer. And the coefficient or constant is basically this front part, this a, the x right here, this is our variable, and then the k in this case represents the degree or the power. And the constant a is called the coefficient of the monomial, and if a is not equal to 0, then k is the degree of the monomial. You guys should also know that by looking at a monomial or a term of a polynomial here, you should be able to identify the coefficient and the degree. So if you do not know how to identify the coefficient or the degree, you should definitely copy this table down and review it to make sure, and make sure you contact me and ask me questions if there is one of these problems here that you're looking at and you're saying, I have no idea why that is the case. And last but not least, definition of a polynomial. A polynomial is basically just going to be a monomial or the sum of monomials. And then these are just different examples of polynomials that you could have. And whether it's a monomial, a binomial, or trinomial, remember all of those are still classified as polynomials. They still fall into the category of polynomials. So Basically, we're going to be working with these type of functions that contain these polynomials within them. And it's good to know all of those prerequisite skills that you've already learned from algebra. Once again, if any of the things that I mentioned here don't look familiar to you, then I would just go ahead and copy them down. And don't feel like, oh, she said it was from algebra and I'm supposed to be in intermediate algebra or college algebra or in any math that you happen to be in. That's okay. It's okay if you didn't learn something the first time around. You can still go back and learn it the second time around. So copy it down so that way you know it. Okay, determine which function is a polynomial function. For those that are, write in standard form and then state the degree, the leading coefficient, and the number of terms. So starting off with this first one right here, it looks like oh, I don't know. You guys tell me. What do you guys think? What do you guys think of this? How does this look to you guys? Does that look like a polynomial function to you? If I were to rewrite this, another way to rewrite this this is not, take that back. Another way to rewrite this would be to rewrite it as 1 minus 1/2 x raised to the negative 1 power. Or 1 minus x to the negative 1 power over 2. So now what do you think? Do you think that looks like a polynomial function? Remember, we said that the powers on the x's had to be I referred to them as either whole numbers, or they had to be values that are greater than or equal to 0 and integer values. So it has to fall into one of those two categories. And here, because this is a negative 1 power, this does not satisfy that definition. So maybe another way that we could have thought about this is if you see here, you have an x, and the x in the denominator has to, it can't actually have like a negative on it because then it would move to the top. So if you end up with a variable that's going to be in the denominator with a positive power in the denominator, then that's not going to be a polynomial function. So this is going to be not a polynomial function. And I always like to box my final answer. All right, next one. F of x is equal to x times the quantity x minus 1. Now for this one, I'm going to distribute this x just so that it's a little bit easier for us to tell if this is a polynomial function. This will turn into x squared minus x. What do you think now? Let's look at this and see. I look at the powers and I see that the powers on all of these x's are integer values that are greater than or equal to 0. So these are going to be satisfying those. These are another way to call them, whole numbers, I think is the easiest thing to just refer to them. Or you could refer to them the way the definition did, integer values that are greater than or equal to 0. And therefore, because those x's, they're in the numerators, we can say, yes, this is a polynomial function. So I'm going to say yes. This is a polynomial function. Now, we're not done. It says we have to write it in standard form. Well, when I distributed the x, I actually did end up writing it in standard form. So I actually got that part done. So I'm going to just copy it down right here. F of x is equal to x squared minus x. So this would be our standard form. And then it said state the degree, leading coefficient, and the number of terms. So I can tell by looking at the highest power that the degree of this is going to be 2. So I'm going to go ahead and write that down. The degree is equal to 2, or we could say it's a second degree polynomial function. And then it said leading coefficient. The leading coefficient, when we write this in descending order from the highest powered variable to the lowest, that's what I used to take as the leading coefficient. So this would be the first coefficient on our leading term. So this is going to be I should write down here. Maybe I should use a different color. There's a 1 here. This is our leading coefficient. So we're going to go ahead and write that down. We have a leading coefficient that is equal to 1. And last but not least, the number of terms. Well, if you look at number of terms are going to be separated by plus and minus signs. So I can tell that this actually has 2 terms in it because there's a minus sign separating 2 terms here. Or maybe another way to think about this, you could write it like this: f of x is equal to x squared plus a negative x. So that way you can see the 2 terms here. So if I put a plus in between them, you can see so that way you know that that second term is negative. So this one has 2 terms. So there, now I've answered all of the questions. So I'm going to go ahead and box all of this good stuff in. All right, let's go to the next one. So here we have the definition of a power function. A power function of degree n is a monomial function of the form f of x is equal to a times x to the nth power, where a is a real number and a cannot equal 0, and n is greater than 0 and it's an integer. Okay, so once again, this goes back to that idea that we were talking about when we're working with polynomial functions. But in this case, because there is nothing else being added to it, we do need to have a variable in there. That's why it can't equal 0. You can't have it be equal to a constant, because if you have f of x equal to just a constant, there's no variable on it, then that means you have a horizontal line, and that would not be considered a polynomial function. So we need to make sure that in this case, for this particular definition for a power function, our n here, in this case, is strictly greater than 0. Can't equal 0. All right. Okay, properties of power functions. F of x is equal to x to the nth power. N is a positive even integer. So some of those properties are going to be f is an even integer. F is an even function, so its graph is symmetric with respect to the x-axis. Properties, let me just put this here. Properties of power functions. F of x equals x to the nth power. N is a positive even integer. So some of these properties include f is an even if. Properties of power functions. F of x is equal to x to the nth power. N is a positive even integer. So these properties are: f is an even function, so its graph is symmetric with respect to the y-axis. Next, the domain is the set of all real numbers. The range is the set of non-negative real numbers. Next, the graph always contains the points -1, 1, 0, 0, and 1, 1, right? And that's because we're working with f of x is equal to x to the n. It's got to be, basically of this form in order for that to happen. So notice that it does have a coefficient of 1 in that case. So that's why we're working basically with the simplest general form of a power function. As the exponent n increases in magnitude, the graph is steeper when x is less than -1 or greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. End behavior. So here where it says this notation, as x approaches -infinity. Let me go ahead and write that out in words for anyone that needs to see that written out. So this means, the way we would say this, as x approaches, I feel like I want more space. How about if I put it up here? As x approaches -infinity. Okay? Then this is saying that f of x, which is equal to x to the nth power, is going to approach positive infinity. So even though x is going to -infinity, x is getting very small, right? The y value is going to go to positive infinity. So we could say here, f of x approaches infinity. Or another way we could say this, f of x goes to infinity. Or another way we could say this, f of x gets very large, right? Very large in terms of positive numbers, right? Very large. So just different ways we can say the same thing with those symbols. And then, so this was basically how we say this first one. I'm not going to write out the second one because I think you guys get the idea there. So I'm just going to read it out loud. As x approaches infinity, f of x, which is equal to x to the n, approaches positive infinity. So if we substitute very large positive numbers, our y values will give us very large positive y numbers. So that's basically what it means. Okay, we're ready to go on to the next problem here.
All right, this is problem number 3. It says use a graphing utility to graph the following power functions. And what I'm going to do is I'm just going to go ahead and graph all 3 of them at once. And I'm just going to copy and paste the graphs on the notes. So this is y is equal to x squared. Let's fix that graph by going to number 6 here, the zoom standard. I'm going to go ahead and take this. I'm going to copy the graph. There it is. And now I'm just going to paste it on the notes. And this is going to represent that first power function. That first power function, a f of x is equal to x squared. Now let's graph the b. B f of x is equal to x to the 4th. So I'm just going to go back to the y equals, y sub 1 is equal to x. I'm going to change that x squared to x raised to the 4th power. We're going to graph it. And this one, you know what I'm going to do is I'm going to adjust the window a little bit because look, notice how when we get close to the origin, it flattens out a little bit. I want to make sure it's very obvious that that's what's happening for everyone here. So we're going to go to window and I'm going to make the X minimum value a -5 and let's do the X max +5. And let's also do the Y min -5. So now when we do the graph, this is, I think, much more obvious that as you're getting closer to the origin, it's flattening out. Okay, let's go ahead and copy this graph. And we're going to go copy and paste. And there's our graph. Good. And then our last graph, C, it says f of x is equal to x to the 6th power. So we're going to go ahead and go y equals, and instead of x to the 4th, I'm going to put x to the 6th. And then we're going to go graph, and there's our graph. And look at the origin. Look how it's closer to the origin. It just flattens out even more. Look at these table of values. Look at as x gets larger. Look at how y gets larger. See? So I just want you to recognize that too, because I'm going to be referring to how, these values of x, what's happening to, as x gets larger, what happens to the y. Okay, so we go copy and paste. And there are our graphs. Excellent. Okay, now let's go ahead and explore the properties that we have mentioned above. So this graph, you know what I'm going to do before I do that? I'm going to actually fix the y equal to x squared so that it has the same window measurements that my other ones had. That way, as we're comparing them and we're looking across all of them, you know, to easier, a better basis for comparison. Got the same window measurements. I'm going to erase that old graph. And there we go.
X goes to -infinity, how f of x goes to infinity. You could also do that on the table of values. So here, looking at this graph that we have here, I'm just going to draw little arrows here because those of you that know me, you know that I like to see little arrows on functions, especially if they do not end, if they keep going on. So I'm going to draw my arrows. So this represents my function f of x is equal to x squared. I can see here by looking at this function that as, let me use maybe a different color here. As this is the x-axis, the horizontal axis, as x goes to -infinity, this is showing me that this is going up towards +infinity for the y. And as x goes to +infinity, I can see here that this is going to go up towards +infinity for the y as well. So this is representative of what we were just talking about. So this is basically saying here, as x approaches -infinity, f of x approaches +infinity. And as x approaches +infinity, f of x approaches +infinity. The domain for this function continues to be all the reals. I know they didn't ask for that, but I don't want you guys to forget this. Set of all x such that x is an element of the set of real numbers. And the range is going to be basically the non-negative numbers, or the set of all y such that y is greater than or equal to 0. And we could also, of course, write those in interval notation, but I'm just going to go ahead and leave it like that. Okay, f of x is equal to x to the fourth. I'm going to go ahead and draw my little arrows because I like to see those arrows in there. So once again here, we can see what's going on. This horizontal axis represents my x-axis. As x goes to negative infinity, this is going up towards positive infinity for the y, right? Or for f of x. And as x approaches positive infinity over here, this is going up towards positive infinity. So it looks like whenever this power on our power function is even, this same thing is going to continue to happen here. So once again, as x approaches negative infinity, f of x approaches positive infinity, right? Because whenever you raise a negative number to an even power, it's going to end up being positive. And when x approaches positive infinity, f of x is going to approach infinity as well. The domain and the range are going to remain the same for this function. And our last one here, f of x is equal to x to the sixth power. I'm going to draw arrows here because I like to see those arrows. So once again, our horizontal axis here represents our x-axis. This is supposed to be an x. I don't want it to look like, I just want to draw my x's. I tend to draw, I don't want it to look like it's a negative x. I want just x. So as x goes towards negative infinity, it looks like this function is going up towards positive infinity for the y. And as x approaches positive infinity, it looks like this function is going to approach positive infinity as well. So let's go ahead and write that down again. As x approaches negative infinity, f of x is going to approach infinity. And as x approaches infinity, f of x is going to approach infinity. Our domain for this particular function, all the reals. And our range is going to be set of all y such that y is greater than or equal to 0. There we go. Properties of power functions. I know what you guys are thinking. They're like, we already did this. No, we didn't do this one. We were focusing when we had, right? What type of power? Even, right? Even integer. So now we're focusing on odd. So properties of power functions. F of x is equal to x to the nth power, and n is a positive odd integer. Properties are going to be the following. F is an odd function, so its graph is symmetric with respect to the origin. The domain and the range are the set of all real numbers. The graph always contains the points -1, -1, 0, 0, and 1, 1. As the exponent n increases in magnitude, the graph is steeper when x is less than -1 or x is greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. And behavior. I'm not going to write the way we say this out loud because we already wrote it out earlier, so I'm just going to just say it. As x approaches negative infinity, f of x, which is equal to x to the nth power, approaches negative infinity. So this time, right, when you take a negative number and you raise it to an odd power, you're going to get a negative number. All right, and as x approaches infinity, f of x is going to approach infinity as well. So let's go ahead and look at some of these here.
All right, so we're going to go ahead and do number 4. It says use a graphing utility to graph the following power functions, and we're going to explore the properties mentioned above. So I went ahead and I increased the speed a little bit here because I think you guys already know how to pretty much input these into your graphing calculator already. And I also decided on these examples to go ahead and not only am I going to make sure you adjust your window, by the way, because remember these are negative. I mean, these have we are including some of those negative y values here because these are odd power functions. So you might want to have to fix that window from that last time we were working with those even power functions. Not only am I going to do the graphs, copy and paste the graphs on the notes, but I am also going to copy and paste the table of values. You know, I didn't do it for the last problems, but maybe I should have. Let me fix this table of values a little bit here. I want you to see how these values change as x gets very large and when x gets very small. So for this one, if we go to -5, you can see, you know, oh yeah, I can see what's happening to the values, but let's go even larger than that. Why don't we have the value here for the table start begin at, let's say, -100, and let's increase the increment of change by, let's say, increments of 20. How about now? Can you really see that difference now? Look at what's happening here with these table of values, right? The larger x gets, look how big y is going to get, right? And the smaller x gets, look how small y is going to get. 1e to the 6, that's just an scientific notation. I'll explain it right now. I'll write it out for you guys in case you're looking at this and you're saying, I don't know what that 1e to the 6 or 1e6 means. I'll write it out for you. There we go. So now we have our table of values right here. And I'm going to go ahead and, like I said, I promised I would explain to you about that scientific notation, so I will. Oh, but first, you know what? Let me do it for all 3 functions. I'm just going to go ahead and graph all 3 functions at once so I don't have to keep coming back and doing the graphing portion because it is a lot of work going back and forth with the graphing calculator. So I'm just going to do all the graphs at once. So that's going to be the graph for f of x is equal to x to the 5th. Notice how it flattens out more as you get closer to the origin here with the x to the 5th in comparison to the y equal x to the 3rd. Look at the table of values. You can see that these are definitely getting much larger, right? As x gets larger, y is getting much larger, right? And our last one. This is f of x is equal to x to the 7th power. So I'm going to go to the y equals. I'm going to change this x to the 5th to x to the 7th. And let's do the graph. So as we do the graph, look at how it flattens out more as it gets closer to the origin. Let's copy and paste this to our notes. And now I'm just going to copy and paste the table of values as well. All right, we've got them all there. Excellent. So there we go. I will explain what these table values mean, okay?
Number 4, use a graphing utility to graph the following power functions and explore the properties mentioned above. F of x is equal to x to the 3rd power. So I already went ahead on the graphing calculator and I already graphed these, and I also copied the table of values so that you guys could actually see what's happening as x gets very large. So you can tell here as x goes to -infinity, y is going towards our -infinity as well, because when we have something that looks like this, negative 1 e6. That's actually scientific notation. It means negative 1 times 10 to the 6th power, right? So that means it's like you have a negative 1 times, let me count the zeros here. 1, 2, 3, 4, 5, 6, 6 zeros. So it's like you have negative 1 times a million, which is going to give me negative 1 million, right? That's a very big negative number. So you can see as the larger x gets in the negative direction, the larger the y value is going to get in the negative direction. And the same can be said the larger you go into the positive direction. The larger that x gets in the positive direction, the larger that y is going to get in the positive direction as well. So 1e to the 6 is going to be the same thing as 1 times 10 to the 6th power, which is just going to be 1 million. All right, let me draw my arrows here on my function before I forget. So we can see that the same thing here is happening with this function, or something similar is happening here that was happening with some of our other functions. Let me go ahead and look at this graph. So this is our x-axis. As x approaches negative infinity, this is going down towards negative infinity for our y-axis. So I can see that as x approaches negative infinity, f of x approaches negative infinity as well. And as x approaches positive infinity, it looks like our function is also going to approach positive infinity. So let's write that down. As x approaches positive infinity, f of x approaches positive infinity. The domain for this is going to be all the reals, right? That's what it's going to be for every single one of these polynomial functions. But I just feel like some of you guys, the more times you write this down, the more it's going to sink in, right? And yes, you could also write that as all the reals this way as well, right? So you could write it this way or this way. And the range, well, when you have an odd exponent, right, on these power functions, it's also going to be all the reals, because now you are also allowed to have negative values. You're not going to be raising all those negative values to an even power. You're raising them to an odd power, which will give you negative values. So now our y can also be an element of the set of real numbers, right? Or you could also write it as the open interval from negative infinity to positive infinity. All right, the next one. So the same thing here. I don't think I need to probably go into detail again about everything. I think you guys can tell by looking at the table what's happening here. And I can think you can also tell by looking at this graph what is happening here, right? So my x-axis, as I'm going to negative infinity, this is going down towards negative infinity for our y-axis. And as I'm going to positive infinity, this is going up towards positive infinity, right, as well. So, and we can see that by looking at our table. If our x's, they get very small, right, they go in the negative direction, we see that our y values also get very small. And if we go in the positive direction and our x values get very large, then we also see that, oh, look, our y values are also getting very large. So it's starting to make sense. As x approaches negative infinity, f of x is going to approach negative infinity, and as x approaches infinity, f of x is going to approach infinity. And our domain is going to be the set of all reals, the set of all x, such that x is an element of the set of real numbers. And our range is going to be the set of all y, such that y is an element of the set of real numbers. F of x is equal to x to the 7th power. Same thing. The only differences you see here with these graphs is it looked like they get larger much faster, you know, here when you were raising these to the exponents, because like if we're comparing these here, like this one, 1 times 10 to the 10th power, that's a 1 with 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the number that's going to when x is 100. And then look at this one. Now this is a 1 with 14 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So they're getting even larger, like faster. And then as they get closer here to the origin, this area, you see how this one flattens out more than the other two? It's getting even closer because those values are so small. And when you raise a small value to a high exponent, it's going to make it even smaller. It's going to make it even get closer to the x-axis, right? So that's what is going on here with these functions. So once again here, this is my x, this is my y. As x approaches negative infinity, this is going to approach negative infinity. As x approaches positive infinity, this is going to approach positive infinity. So as x approaches, oops, I meant to say, I want to write the negative infinity first. I know, it's a infinity. There we go. Looks a little neater. F of x approaches negative infinity, and as x approaches positive infinity, f of x approaches positive infinity. And once again, our domain remains the same. You can see that my writing is just getting worse as these notes go along. And, I want to really apologize for that. Sometimes I make these videos and I'm a little bit tired. You can tell which videos I'm like more energetic on because I think you can hear it in my voice. And then you can tell which videos I'm making at the end of the day because I just think it's very obvious. I can't hide this stuff. Identify the real zeros of a polynomial function and their multiplicity. So when we are looking for real zeros of a polynomial function, we're going to be looking for basically the x coordinates of the x-intercepts. So it's these values here, these x, every time you have an x-intercept, the x coordinate of the x-intercept is going to represent R0. And we've got our definition right here. Real zero, if f is a function and r is a real number for which f of r is equal to 0, then r is called a real zero f. So the way I kind of like to think about it, when you were taught in elementary algebra about that function machine. No, you guys don't remember that? Remember you were taught there was like a function machine that if you gave it an input and then it provided you with an output, something like this. Yes, and this is our function, f of x. So it's basically, this is what it's saying here. It's saying if you input like this, they're calling it r. If you input this value of r, and then it gives you this value of 0 over here, we're going to call this r value here, we're going to call it a0. I know that you're like, but that's value probably isn't a 0, and you're right, it probably isn't a 0. It could be a 0, but the fact is that it produces a 0. So what we like to call, in algebra, what we like to call those values, those x values that produce y values of zeros, we like to call those values 0. I know it sounds weird, but that's just what it is. So if I were to think of this as an ordered pair, this would basically be r comma 0. Anything where the y value is a 0 basically represents an x-intercept. So we're basically looking at the x-coordinate of the x-intercept, and that's going to represent our zeros. Yes? Maybe I should write that up here somewhere. Can I move this up here? We call this value a 0. Okay? Because it produces a y value of 0, if that helps. Yes, and I hope it does. Yes. I know. As a consequence of this definition, the following statements are equivalent. R is a real zero of a polynomial function f. R is an x-intercept of the graph of f. I like to call it the x-coordinate of the x-intercept. For those of you that know me, an x-intercept to me is an ordered pair. It's not just the x value, but every textbook's a little bit different. And this, I took it out of the textbook. So if it were me writing this textbook, I might just be a little bit more specific, and I might just say this: it's the x-coordinate of the x-intercept. And I would like that a little bit better. X minus r is a factor of f, and r is a real solution to the equation f of x is equal to 0. Yes. Okay, let's go ahead and go on. Should I leave it like that in case anybody wants to copy that down? Yeah, maybe I should. Form a polynomial whose real zeros and degree are given. Answers will vary depending on the choice of a leading coefficient. We're just going to go ahead and choose a leading coefficient of 1, because that would be the easiest, I think, to work with. So we're going to have our leading coefficient equal 1. Yay! Okay, so here, these are the zeros. This is the degree. So this is going to help us in creating our polynomial function.
So we left off here where we're trying to form a polynomial whose real zeros and degree are given. We're going to have to use this information from up above where it says x minus r is a factor of f. That's an important piece of information. So we're going to have to definitely use that piece of information there. What else? Well, if I'm going to have to write things as x minus r for my factors, I'm going to have to basically substitute those zeros in for that r part, right? So I'm going to need an x minus r for each factor that I have inside this polynomial function. And because it's a degree 3, I'm basically going to need to have 3 factors. So, because that's what the degree 3 means. It means we have 3 factors within that polynomial function. So the general form of this is going to have to look something like this. F of x is equal to a. We had already decided that we're going to choose a, our leading coefficient, to be a 1. So I'm going to be substituting a 1 there. And then we're going to have an x minus r sub 1 times an x minus r sub 2 times an x minus r sub 3. 3 factors. Let's go ahead and substitute. For r sub 1, we're going to substitute negative 4. R sub 1, negative 4. R sub 2, 0. And r sub 3, 2. All right. Let's go ahead and do this substitution. So now we're going to go ahead and substitute all of this good stuff in for each one of these. So it's going to be f of x is equal to, instead of a, it's going to be 1 times x minus negative 4 times x minus 0 times x minus 2. Let's simplify this a little bit. I don't need to write down that 1. And that x minus 0 back there, I could write that just as an x out in front. And x minus a negative 4 is the same as x plus 4. And then we just have x minus 2. So there we go. That's our function. We have written out our function. Not too bad, huh? Kind of fun. Definition, real zero of multiplicity m. If x minus r quantity, all raised to the m power, is a factor of a polynomial f, and x minus r raised to the m plus 1 is not a factor of f, then r is called a real zero of multiplicity m of f. We're going to form a polynomial whose real zeros and degree are given. Answers will vary depending on the choice of a leading coefficient. The easiest leading coefficient to choose is 1, so I'm just going to go ahead and choose a 1 for that. This particular problem says our zeros is -2 multiplicity 2, 4 multiplicity 1, and then degree 3. When it says multiplicity 2, it just basically means that we have 2 factors, right, pertaining to that zero. And 4 multiplicity 1 means we just have 1 factor pertaining to that 0 of 4. And degree 3? Ultimately 3 factors, right, that are going to make up this polynomial function. So let's go ahead and start writing this. A is going to equal 1. That represents my leading coefficient. That's the easiest one to choose. So that's what I'm going to substitute for my a part. So f of x is going to equal a times x minus r sub 1 times x minus r sub 2 times x minus r sub 3. I'm just going to go ahead and do the straight substitution here. So it's going to be 1 times x minus a -2, x minus a -2, and then x minus 4. Notice I put 2 of those same factor because it said it had multiplicity 2. Let's simplify it to say x plus 2 instead. And to simplify it even further, I could just write this as f of x is equal to x plus 2 quantity squared times a quantity of x minus 4. This would be the simplest way to write it, all right? So these are not too bad, right? They're kind of fun. Find the polynomial with the given zeros whose graph passes through the given point. Zeros are going to be -2, 0, 2, and the point is -4, 16. A, we don't know what a is, and we can't choose whatever we want. We actually need to find what a is equal to. So we're going to have to find this specific leading coefficient that's going to create the case that was given to us. I'm going to write down that general form for a polynomial function. F of x is equal to a times the quantity x minus r sub 1, but instead of r sub 1, we're going to write -2. Actually, let me write the r sub 1 just to take it step by step. I'll take it real slow here, and then x minus r sub 2, and then x minus r sub 3. There. Now we're going to substitute everything that we basically know. Our r sub 1, our r sub 2, our r sub 3, we know what those are. And the x and the f of x, we know what those are too. So we're just going to do a bunch of straight substitution. It's going to be 16 equals a times -4 minus a -2 times -4 minus 0 times -4 minus 2. Now let's simplify this as much as we possibly can. -4 plus 2 times just -4 times -6. So this is going to be a times -2 times -4 times -6. If I multiply all of those 3 factors together, -2 times -4 times -6, what do I get? Well, -2 times -4 is +8, and +8 times -6, that's going to give me a -48. So we're going to go ahead and write -48a. Let's divide both sides by that -48. So if I divide both sides by -48, I'm going to get 16 divided by -48, and that will reduce to, well, let me do the reducing over here on the side for anyone that needs to see this. I'm going to use prime factorizations. Prime factorization of 16 is going to be 4 factors of 2. 2 times 2 times 2 times 2. And the prime factorization of that -48, well, it's right up here, right? 2 times 2 times 2 times 2 times 3. Oh, and let's not forget the negative. So this is going to simplify to -1/3. So my a, my leading coefficient, is equal to -1/3. Now that's what I was missing. Now we're ready to plug it in. We can actually write out our polynomial function, right? So let's go back to our polynomial function. F of x is going to be equal to -1/3 times x minus that -2 times x minus 0 times x minus 2. And let's just simplify it a little bit more. F of x is equal to negative 1/3 times x plus 2. Oh, I forgot to write the x in the front first, because for that x minus 0, and then we'll write x plus 2 and x minus 2. And there we go. There you have it. There's our polynomial function. Fun stuff. Yes, right? We don't miss out on the fun here in math. It just keeps coming. You know, can't keep it from being fun. It just is. All right, turning points. If f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. If the graph of a polynomial function f has n minus 1 turning points, then the degree of f is at least n. So let's talk about turning points. What is a turning point? And what does this mean when it says it's of degree n, then the graph has at most n minus 1 turning points? What does that mean? Well, let's go back to this one graph right here. Let's see what are turning points in this graph. So a turning point would be like this point right here at the very top right here, and then it goes down, and then it turns back around, it goes up, and it goes down, and then it turns, and it goes back up. So if we were to count all the turning points in this particular graph, we have 1, 2, 3, 4 turning points where it changed direction, where it went from either increasing to decreasing or decreasing to increasing. So that's what we call a turning point. So I could tell you that this polynomial, because it has 4 turning points, then the least degree that it could have is a 5. Okay, so that's a turning point. All right, end behavior. The end behavior of the graph of the polynomial function, of this polynomial function, is going to be the same as that of the graph of the power function. So basically, it's the leading coefficient that's going to tell you what the graph is going to look like. You just have to look at that leading coefficient with that leading term, I should say leading term, and along with the leading coefficient, with the with the whole leading term and the degree. And that's going to tell you what the end behavior of any polynomial function is. Okay, let's start working with one of these polynomial functions. Let's list each real zero and its multiplicity. Well, let me copy this down. We have here x plus 4, and I'm going to set it equal to 0, and x plus 3 set it equal to 0, because sometimes I like to do this to help me find my zeros. So this is going to be r is equal to negative 4, so this is going to be my 0. And over here, same thing, minus 3, so x is equal to negative 3. I'm not going to write r equals negative 3. We're just going to now note that we refer to this as a 0. So this is going to be our zeros. And the multiplicity is going to be the exponent that's on that factor. Since x plus 4 has a second a power, or a power of 2, it has multiplicity 2. And since this x plus 3 has a power of 3, we would say that this 0 has a multiplicity of 3. Let's go ahead and write out our answer so it looks a little bit nicer. So we're going to write out that what our zeros are. So I'm going to make sure I write out here my zeros are going to be equal to negative 4. And that negative 4 is going to have a multiplicity of 2. And negative 3, and that negative 3 is going to have a multiplicity of 3. And that's going to be the way I'm just going to write out my answer there. All right, B, determine whether the graph crosses or touches the x-axis at each x-intercept. Crosses means it's going to go like across the x-axis. Touches, it's just going to like touch it and bounce off. So it's kind of like what we would say it's tangent, another word for that. Why don't I go ahead and I need some space to write this out. I apologize here. And I apologize overall for this video. My editing on this video is probably not the best, This video has taken me a long time to try to complete it, and I've been trying to find techniques to be a little bit more efficient with my videos, but I'm not there yet, you guys. You know, I'm not. I'm doing my best. All right, so f of x, we're going to say this is going to be kind of the rules for when f of x touches or crosses the x-axis. How to know if it's going to touch or cross based off of looking at the polynomial function. So if it touches, we're going to see here that if r is a real zero of even multiplicity. Remember what even means, right? Even power on that factor of that zero, right? That's what it means. Then that's going to mean that at that x-intercept, that our function is going to touch the x-axis, like touch and bounce off, right? Or be tangent at that point of the x-intercept. So that's what it means when you have an even multiplicity on that zero. All right, so let's think about how we can write this out so it sounds nice, right? Even multiplicity. Even, that means even power. If you need to write that down, write that down. So this means the graph of f of x, oh sorry, we'll just say of f, touches the x-axis at r. Touches means like it bounces off. Okay, if you need to write bounces off in there, you write that in there. If you need to write tangent in there, you write that in there. All right, the next one. If r is a real zero of odd multiplicity, that means it's going to have an odd power on that factor for that zero, right? Odd numbers are like 1, 3, 5, 7, 9. Then this means that the graph of f crosses the x-axis, right? It's going to go across the x-axis at r. So that's what it means. Maybe I could draw a little sketch here. So here, these first 2 points, they cross. The last one touches. So this last one that I drew here, this is, I could tell that this zero is of even multiplicity because it only touches the x-axis. So I'm going to write here, this touches, right? And this zero has even multiplicity, right? Like an even power on the factor, right? That's what it means. If you need to write bounces off or is tangent at that point in the note, write that in there as well. Odd multiplicity means it crosses, so I can tell on these first other two x-intercepts that it has odd multiplicity because it crosses the x-axis. So I can tell that this zero has odd multiplicity. Okay, so that's how we can tell whether f of x is going to touch or cross the x-axis, is by focusing in on those zeros and looking at the multiplicity of them. So looking back at this problem right here, I'm going to have to look at the multiplicity of each of these zeros. So here I had -4 times x plus 4 quantity squared times x plus 3 quantity cubed. Looking at this first one, I can see that this one has a 0 of -4, and I can see the multiplicity. The multiplicity on this is a 2 because it's squared, and because it's an even power there and it has even multiplicity, we say that it touches the x-axis. So it's just going to touch the x-axis at that point. And then for our second one here, our second zero, I would focus once again on the factor of that polynomial. So the second factor of this polynomial is going to be that x plus 3 quantity cubed. So why don't we go ahead and go back to that and highlight that in green. And we're going to say this 0 is equal to negative 3. The multiplicity on it is going to be 3. Because that number is odd, I know it's going to cross the x-axis at x equal to negative 3. All right, so let's go ahead and write out that answer so it looks a little nicer. So we're going to say that this graph touches the x-axis at, and let's write here negative 4. Let me scoot this over so I have enough space there. So this graph touches the x-axis at negative 4 and crosses the x-axis at negative 3. All right, let's go ahead and box that in as our final answer. All right, part C, determine the maximum number of turning points on the graph. For this one, we're going to have to use what we learned about turning points. It says here that if it's degree n, the graph f has at most n minus 1 turning points. So based off of the degree, you're going to subtract 1 from that degree. And that's going to give you the number of maximum turning points. Our degree for this one. Well, in order to determine the degree, we're going to have to look at the powers here. We had a 2 and a 3. I'm going to add those together, and that's going to give me degree 5. So if I were to multiply all these x's together, they would ultimately come out to x raised to the 5th power. And if I go 5 minus 1, I get 4. Therefore, I know that this function is going to have at most 4 turning points. So the maximum number of turning points is going to be equal to 4. D, determine the end behavior. That is, find the power function that the graph of f resembles for large values of absolute value of x. So to determine the end behavior, we're basically trying to figure out what is our function going to look like in the end, just kind of an overall general appearance of this function. Well, if y is equal to x raised to an even power, I know that the overall general appearance is going to look something like this. It's going to go upward like this, but we might not know what's going on in the middle part. And if y is raised to x raised to an odd power, it's going to look something like this. So for this particular function, what we need to focus on primarily here is we need to focus on the degree. It's odd, so I know it's going to look like this one right here. And I also need to focus on the leading term, leading coefficient too, right? Because depending also whether it's positive or negative, it might be reflected, right, across the x-axis. So in this case, f of x is going to be equal to x to the 5th, but wait a minute, I think we had a different coefficient here in the leading coefficient spot. So I think this is f of x is equal to 4x to the 5th. And I think, yes, that's what it says here we need to focus on for end behavior, is that first leading term of your polynomial. So the end behavior of this function is going to look a lot like that y equal to 4x to the 5th for that power function. So let's write that down as our answer. End behavior is the same as y equal to 4x to the 5th power. Okay, number 9. Identify which of the graphs could be the graph of a polynomial function. For those that could, list the real zeros and state the least degree the polynomial could have. For those that could not, say why not. Looking at this first one, why don't I go ahead and label this A and label this second graph B? All right. This one is a yes. Yes, this could be a polynomial function because polynomial functions are continuous everywhere. And there are going to be like no sharp corners or sharp turns on a polynomial function. It's going to have just like smooth curves. I can see here that we have basically two zeros. We have one at x equal to -1 and here one at x equal to 2. So I'm going to write down my two zeros. And then I also need to state the least degree. So let's count the number of turning points. 1, 2, 3. So since I have 3 turning points in this polynomial, I know that this 3 is equal to our n minus 1. Let's solve for n. So this is going to give me n is equal to 4. So the least degree of this polynomial would be 4. Let's box that in. And let's look at the second one. So first question here, is this a polynomial function? Well, look at this sharp corner that's going to happen here at x equal to 0. Because there's a sharp corner at x equal to 0, I can tell you this is not a polynomial function. So we're just going to go ahead and say here that this could not be a polynomial function. And the reason it could not be a polynomial function is because it has a sharp corner at x equal to 0. And remember, if you come across any functions that have any gaps, any holes, you know, those are also would not be considered polynomial functions. All right, so we're done with that. Let's go to our number 10 problem here. 10. Construct a polynomial function that might have the given graph. Well, let's count the zeros. We have 3 zeros, and those zeros are going to be -1, 1, and 2. And let's also count the number of turning points. It's got 2 turning points. So I know that number of turning points, that's going to help me determine the degree. So the least degree of this polynomial would have to be 3. And this polynomial has to be odd because I can tell by the way the shape of it is going, it's coming from up and it's going downward. And because it's flipped around from that regular one that I drew, this is actually going to have a negative coefficient because it's been reflected across the x-axis. So let's go ahead and write down what our possible polynomial function for this could be. I'm going to write down the general form of our polynomial function here. And then we're going to do our substitution. For the a, I'm going to just use a -1. And then r sub 1 is going to be -1, r sub 2 is going to be 1, and r sub 3 is going to be 2. And now let's just simplify it. And oh yeah, this makes sense because the number of turning points we had said was 2, so therefore n is 3. It's an odd degree, and here I've got 3 factors. So x, if I multiply this out, it would end up being x to the 3rd. So it looks good. So if I simplify this out, this is what I get. So this would be my final answer right here. All right, good job, you guys. Thanks for hanging in there for the whole thing. Good.